Doing every challenge question. This is the last chapter in Core Pure 2. It's the review chapter 2. Let's just do it. Proof by induction here. So clearly this works for n is 1 because m equals m. So that's fine. So we're going to assume that it's true for n equals k. So we're going to assume that this is true. And then we're going to investigate what happens if we let n equal k plus 1. Well, of course, m to the power k plus 1 can be written as m to the k times m. M to the k by the assumption set is just m, so all I need to do now is do m times m, which is of course this times itself. And if I can show that equals m, then I am done. So let's multiply these. It's this times this plus this times this for the first bit, and then this times this and this times this for the second bit, which is just the same thing. And then this for this next bit, and then this for the next bit, which is the same again. If you factorize out cosh squared from this term, and then factorize out sinh squared from this one and this one, in fact minus sinh, I guess, then you'll get all of these things. And all of these things are equal to 1 because cosh squared minus sinh squared is 1. And you end up with this, which is m, and so therefore it's true for all integers n. Good. Next question. Solve this system of simultaneous equations here. So what I'm going to do is I'm going to take this one here and differentiate it. I think that's what I'm going to do with respect to t. So I just wrote it the other way around for some reason, I'm not sure why. Differentiate with respect to t, and now I can shove this result here. Dx by dt is this, but dx by dt is also y. So I have y equals this, which is great. Move this to the other side and get this kind of idea. This is an auxiliary equation of the form m squared minus 1 equals 0. So m is plus or minus 1, which means solutions in terms of for y in terms of t are this here, because you just put a 1 here and a minus 1 there. And that's all good. We can do the same now. We can use that, I guess, to solve for x. Or first, I've got this information, y is 0, t is 0. So you can put that in, you get this. And then I can differentiate it, I guess, with respect to t. And I'll find this here. And now I'm doing that because now look, dy by dt is just x. So I can say x equals this here. And then I can use this initial condition here. X is 1 when t is 0. So say 1 equals a minus b, because each of these t's when t is 0 is just 1. And now, of course, I have this and this here. That means a is a half and b is minus a half. And you can put those results both back into here. And you get y is that, and you get x is this. But then notice that this is just the definition of sinh of t, and this is the definition of cosh of t. So therefore, I think I am done with this. Part B then, another system of differential equations. This one is going to be a little bit harder. I'm going to take this one here and differentiate it with respect to t. So it becomes tq by tt squared equals dp by dt plus dq by dt, just differentiating them all with respect to t. And now this result here tells me that, or this dp by dt, I can replace with p minus q. And that's super useful because I'm going to write it out again for some reason, not sure why, but just sure, that's unnecessary. But what is useful about this is from this line here, I can write p is dq by dt minus q, and I can replace that information in there. And then this all comes together to form a lovely differential equation in q. So this auxiliary equation is going to be m squared minus 2m plus 2 equals 0. I can quickly solve that. For m is this, which means solutions are of the form this, where this number here goes there, an a and a b, and then the 1i, the 1 goes here and here. So that's all good. That's q. Now, you can do exactly the same thing for p. Like, because of the symmetry in these equations, you can do exactly the same work and you'll end up with p as something similar, and you maybe put a c and a d here. But that's not going to get you any real progress because you can't solve for all of those variables. So you actually need to do something that's a little bit more intelligent. I can also say at this point that because q is 1 when t is 0, this goes away when t is 0. This turns into a 1, this turns into a 1, so you get a as 1. So you can write this here. So, okay, how do we make actual progress here? Well, what we can say is let's rearrange this one for q, or for minus q, I guess. And I'm going to say I can actually just solve this straight up for p, because I know what q is in terms of t. So I can, I'm not going to yet, but I'm going to replace that in a second. Firstly, I'm going to use an integrating factor on this. This is just minus 1 lot of p. So if I just integrate e to the power, or do e to the power integral of minus 1, that's minus 1 integrates to minus t. So that's e to the minus t. So if I just multiply this entire equation by e to the minus t, I get this. And this is good for two reasons. Firstly, q, which is this, is going to cancel with this e to the minus t. So you're just going to end up with minus this thing here, which is great. And also this thing here is now just the result of a product rule differentiation of d by dt of p e to the minus t. Because if you differentiate this term first, you get dp by dt into this. And if you differentiate this one, you're going to get minus p e to the minus t, like this. And then, like I said, the e to the minus t cancels with the e to the plus t. Good, so we get this here. We can integrate both sides. And now, of course, I've just integrated both sides here to get this. Now, there isn't a plus c, and I think I can justify the fact that there isn't a plus c because for two reasons. The first reason I can justify it is, like I said, you could do exactly the same working for this and arrive at p equals this thing, which obviously doesn't have a constant on the end. If you just start with this one here and then do exactly the same steps, just with the other equations. So that's my first justification for why I don't need a constant at the end of this. The other justification, I guess, is looking at these two equations here. When you derive q, you don't get a constant. We know q doesn't have a constant in it, and so therefore, if p had a constant, there's no constant over here, there's none here, there'd be nothing for the constant in p to cancel with. So I think that's my justification for why there's no constant here either. Now I can move on. I can times everything by e to the power t, and now I can plug in the information p is 1 when t is 0, and that gets me that b, I think, is 1, in the same way that a was 1 earlier. So we end up with these two equations, which is beautiful, because now we can make some progress on the last equation, r. And to do that, what we'll do, I've also replaced this b with a 1, because it's the same result as this one, so that's cool. So now what I'm going to do is I'm going to take this one, I'm going to replace the p with this thing, and the q with this thing here, so that's all good. You can expand all that out and do some collection, and you'll get this here. You can move the r to the other side, and now I'm going to do exactly the same integrating factor I did the previous time, which was I can just say, or times everything by e to the power integral of minus 1. Integral of minus 1 is just t, so this is e to the power minus t. And that's great because that cancels those e to the t's, which is fantastic. And of course, it creates the product here, which is good. I can group that into this now. It's just the same thing as the one before it. Now I can integrate both sides. I do need a plus c in this case, which I know mostly because I'm looking at the answer as I'm doing this. Of course, at this point, you can times everything by e to the power t, and you can plug the information when t is 0, r is 1. When t is 0, all of this goes away except for this one. So you end up with a minus 1 plus c has to equal 1. So c has to be 2, I think, and we'll be done. And done and dusted with that question. Excellent. And the last question in the whole book is this thing here about polar coordinates. Also a very tricky question. I was unbelievably thrilled when I got this because I did not think what I was doing was going to work at all. And I'm sure you'll see what I mean when I'm doing it. Anyway, x equals r cos theta, y equals r sin theta, because it's polar coordinates. What we're going to do here is I'm going to work out the gradient of this line here. So, of course, the gradient of this line is dy by dx. But to do that, I need dx by d theta and dy by d theta first. Now, r is a function of theta. So when you derive that, you're going to have to do some product rule. Derive this one for dr d theta, and leave that one alone, and then leave this one alone and derive cos theta. And same thing for the other one, which will get you this result here. Now, dy by dx is this one divided by this one, and you could do some KFC, not sure why that came up first. You can do some KFC to show in your head why that definitely works, but in any case, this cancels with this and you get dy by dx. So it's this one divided by this one. And now, why am I doing that? Well, the gradient of this line is rise over run. So if you were to do a little triangle, it's rise over run of this. But also, what else is rise over run of this triangle? Well, it's tan of this whole angle here. And this whole angle here is alpha plus theta. So therefore, the gradient of this line here is the same as tan of alpha plus theta, because of course you're going straight across, and then theta is this is a corresponding angle, right? So tan of alpha plus theta, apologies for that, is equal to this thing here that I've said, the gradient of this line. Now, okay, so that's some progress made there. It's a nice little trick to know that tan of the angle is equal to the gradient of the line. It's just a nice little trick to bear in mind because it helps you out in questions like this. Anyway, what can I do now? Well, I know the double angle or the compound angle rule for tan, right? Yeah, it's this. So what I'm going to do is I'm going to say I can split this side up using this idea into alphas and thetas. And now tan of theta will, the xy coordinate pair we've already written down is r sine theta, r cos theta. So tan of alpha, same thing as being rise over run, is just r sine theta divided by r cos theta. The r's cancel, and it's just sine theta over cos theta. So I'm going to put sine theta over cos theta into these two results. And now I'm going to times the top of this fraction and the bottom of this fraction by cos, just to make it look a bit more simple. And this is how far I got when I realized that this is how far I got on hope. I was high on hope at this point, because all I have to do at this now is just pray that if I actually bother to work through this and rearrange it for tan alpha, I'm just going to somehow end up with this. And it turns out that you do, and this is why I was super pleased with this question. So what I've done here is I'm going to obviously cross multiply all this out to get this. Now I'm not actually going to expand this, because remember, I'm trying to rearrange for tan alpha. So what I'm going to do is I'm just going to do this term times all of this bracket, and then I'm actually going to expand the second two bits. So I'm going to have to use quite small font here, but I'm going to do this times all of this bracket, which is here, and then I'm actually going to expand these two last bits. Same thing over here. So this entire bracket times this is just this bit at the end, and then actually expand out this bit here to make this. And now this is really nice, right? Like this cancels, I believe, with this here, which is great. When you add r sine squared onto both sides, which is what I've done here, you can factorize out the r to leave r into sine squared plus cos squared, which we all know is 1, so that's even nicer, so that goes away. I can also move this over to the other side, left the r there that factorized out, move this to the other side like this, and then factorize out the tan alpha, whilst at the same time multiplying in the cos and the sine, and you'll end up with this. So that's factorize out the tan alpha, multiplying in the cos to there, and the sine to there and there. This cancels with this, which is beautiful. Factorize out the dr by d theta from these two terms, and you get cos squared plus sine squared, which is 1. And you get tan alpha into dr by d theta equals r. Divide by dr by d theta, and you get what's required. Just a fantastic question. Thanks for watching. I'll see you next time.